Imagine a sleek, highly advanced algorithm that processes a massive stream of real estate data and instantly predicts housing prices with 100% accuracy. It never misses a single decimal point. Seeing that flawless output creates the immediate impression of true machine intelligence and total reliability. But there is a fatal flaw operating beneath the surface. This AI is being tested on the exact same dataset it was originally trained on. Simply repeating a value the system has already seen doesn't demonstrate intelligence, it demonstrates memory. It tells us nothing about how the model will handle a situation it hasn't encountered yet. An algorithm built purely on memorization is functionally useless. The moment you ask it to evaluate an entirely new, unseen neighborhood in the real world, its logic will collapse. Think of it like a student who spends weeks perfectly memorizing a list of practice questions, but makes no effort to understand the underlying subject. That strategy falls apart the second they sit down to take the actual final exam and encounter entirely new problems. True knowledge isn't proven by regurgitating the practice sheet. It requires applying logic to a problem you have never seen before. This creates a core challenge for data scientists. How exactly do you administer an objective final exam to a machine learning algorithm? This is a standard machine learning dataset, translating our classroom analogy into concrete housing features like bedrooms, bathrooms, and price. Techniques like feature engineering help us extract stronger signals from this raw information, but even the most precise inputs are worthless if the evaluation is rigged from the start. The solution to this problem is a physical division of the information, separating the dataset into two distinct blocks before the model ever begins its training. We apply a standard ratio. The dataset separates cleanly into a massive 80% chunk on one side and a smaller 20% chunk on the other. That large 80% block is our training data. This acts as the textbook the model uses to study and learn the underlying market patterns. The remaining 20% is our testing data. This block is strictly quarantined. We completely hide it from the AI during the entire training process. Deliberately hiding a portion of your most valuable data is the only mathematical way to guarantee your algorithm receives an honest evaluation. This shows the two-step verification process. First, the model learns using only training data to build logic. After training is complete, we unlock the testing data. The model predicts unseen house values, which we compare against actual hidden prices for an honest score. Executing this two-step verification process doesn't require manually sorting through thousands of rows of spreadsheets. In practice, we use this simple function in Python. This Scikit-learn code automatically separates our housing features and target prices into isolated datasets instantly. That single line of code is the ultimate barrier separating real artificial intelligence from a glorified database lookup. To see why this matters, we have to look at the entire life cycle of a machine learning project, from raw data collection down to the final output. Looking at this machine learning pipeline, the train-test split sits squarely in the middle as the critical checkpoint for the whole system. If a dataset bypasses this specific phase, the model evaluation and prediction stages at the bottom become entirely invalid. A strict split prevents us from building the untrustworthy, fake AI we saw at the beginning, ensuring we output a validated model we can actually deploy. The train-test split doesn't make a model smarter, it simply proves that the model's intelligence is authentic. True machine intelligence can never be measured by how well a system remembers its past. Its value is strictly measured by how effectively it adapts to data it has never encountered before. When building algorithms, you must always reserve unseen data for the ultimate test. You train on the past, you predict the future. Because to predict the future accurately, you must always be tested on the unknown.